Back in Lumberyard, one thing that customers ask us is to improve the build and developer experience. To give some context here, Lumberyard started out of the CRY code base, and as part of that, we received that build system, which was WAF with some modifications that CRY did. On top of that, when we were in Lumberyard, we did more modifications, and we built more things on top of it. The way that WAF was structured is that it's a Python-based build system, and that was put inside the repository. So after we did a lot of modifications, it was somehow hard to take new versions of WAF. So there were some bugs inside there that were related to WAF, and some bugs related to things that either CRY or Lumberyard did. So when we took a step back and thought, okay, how can we make this better? We found ourselves in two different paths. Either we went back and tried to make WAF work, or we considered changing to something else. After analyzing a little bit of what were the reasons why WAF was not working properly, one of the things that we found is that we may need to actually go back, take all WAF out again, take WAF all out and put it a new version, and then start building on top of that again. So if we were going to do that, we just analyze if that's what we wanted to keep using. To give some context, at that point, we were having around 500 targets. We had over 18,000 files, compilation units, so that's CPP files. And we have over 4 million lines of code. Almost 4 million lines of code. My name is Esteban Pab. I'm Senior SD at AWS, and I'm going to be talking about O3DE's build system. So first, I'm going to do an introduction and try to explain the whys behind going to CMake. And then I'm going to dive into our CMake usage and try to give a map of where to find things and why certain things were done that way. So the root of the problem, building C++. So building C++ is quite complex. I simplified in this graph. All the extensions are mostly Windows-based. We have two main parts. One is the compiler, which is composed mainly by the preprocessor and the compiler. There are other parts there, but I oversimplify it to make a point here. And then we have the linking side, which is the linker and the archiver. Those sometimes are different binaries that you execute. So how building C++ works, you basically feed it to the compiler compilation units, CPPs. You also feed it compile definitions, include paths. You also feed it compiler flags. And that internally generates a translation unit where it expands all the includes, all the preprocessor defines, and then it feeds it into the compiler. And that produces an object file. Then you group multiple object files, and you can pass it to an archiver, and that generates a static library. Or you can feed those object files into the linker with other libraries, and that can produce dynamic libraries or executables. So in O3DE, right now, we have over 9,700 C++ compilation units. We have over 450 targets. So if you start thinking about it, if you had to do this manually, it will be over 12,000 invocations that you will have to do to actually get your thing built. So if we wanted to build O3DE manually, it will be over 12,000 invocations that we will have to do. And this is not even considered things like UIC, mock, code gen, resources, and etc. Other things that you also need to generate and pass to the compiler, to the linker to get it done. And the big problem here is, OK, now I have to change a header file. What do I have to execute to get all the changes updated, right? I want to change some header file. How do I find out all the things that get affected by that to produce the new libraries? And the compiler and the linker don't know that. Like, if you call the compiler again, it will just compile again. It doesn't know if the header file changed or not. And this is where build systems get into the picture. Build system orchestrate all this and execute this in parallel and find out which things they have to execute to update what you already built. And there are a lot of build systems out there. So this is a list. I'm probably missing half of them or more. So how do we choose a build system that fit what we want to try to achieve for O3DE and for our customers to provide like a better build experience and be more, and basically to improve the build process. So there were 4 things that we were looking for. One was fast iteration. So gladly, most of the build system focus on that because that is one of the things that the C++ always kind of like had a lack of, to be able to build fast. So most of them will build in parallel, most of them will detect changes, so that is kind of covered by most of them. The second part is important, and is that we wanted to be able to support all the platforms that we have. So we have around 9 platforms that we support, so we want to build a system that can work in all of them. We don't want to be in the, to get into having multiple build systems because that is another set of problems that you will have to deal with, like trying to get all the files sync between them. If you add one file to one build system, you will have to go and update the scripts for the other build system. If you build some feature related to the build system, you will have to build on both of them. So we wanted just one build system, right? And we want that build system to work in all platforms. So that takes some of the list. So for example, CMake, it's a code generator, a script generator, similar to CMake, but it's written in C#. And one of the things is that if you want to run it in Linux or Mac, you have to run it on Mono, and it may not work. Like even in their documentation, it says something like, you may have lag running it on Mono. So we don't want to get into the trouble of trying to make that happen. The third thing is that we want to provide a good experience in each platform. There are some cases where it's very obvious. So for example, an iOS developer, it's very likely that they will want to develop in Xcode, right? You are expecting to be able to develop in Xcode because that has all the tools. It's what Apple wants you to do, and that's what works the best. An Android developer will expect to be able to work on Android Studio. So you are expecting to be able to produce something that will work well in that environment. So at that point, we realized, okay, maybe we are not looking for a build system. We are looking for something before that. And this is where there is a division in what is an actual build system and a project generator. So some in this list are actually not build systems. And CMake is not a build system. CMake doesn't perform the build. What some of these do is they generate build scripts for other build systems to do the build. So we realized at that point, okay, if we want to provide the best experience for all the platforms, we need to find something that generates that experience for every platform. So basically, something that can generate the build system that each platform prefers. And the 4th item that we were looking for is we wanted something that was known, used, that was used in open source, that it wasn't that hard for someone to come in and start using it. One of the issues we had with WAF is that it was not well known, so every time that there was some issue, it was very hard to get developers to go and fix them because it was quite complex and you had to understand it very well to do something. And we also wanted to be well supported and have some community behind it. So from that list, we ended up with CMake. That CMake ended up checking all the boxes there, so that's what we picked. I'm not going to go through this because I already did it in the previous talk. I'm just going to remind you that CMake is not a build system. It's a project generator, so you can argue the name of the talk is a little bit misleading. So when I'm talking about the O3DE build system, what I'm referring to is the O3DE CMake scripts that we use to describe the build, that then will go and generate the scripts for another build system to build. So I'm not expecting you to see this or to read it. This is the entry point. Now we are going to go into somehow a map of how to find things inside O3DE. So the first entry point and where you should start looking at is the root CMake list txt file. There are 3 parts here. The first part is what we call initialization, and this is basically we are including other files and bringing functions and functionalities into our CMake environment. Then we have a subdirectory processing, and this is where we start including other folders that will have targets. So this is where we include things like the code folder, the gem folder. The way that we include the gem folder is through a section that is subdirectories there. External subdirectories. And inside here, we also have a part where we include projects if you are in an engine-centric workflow. And then we have another section that is post-processing. This third section is related to how CMake parses things. So CMake is going to parse the CMake files and all your include instruction and add subdirectory instructions linearly. So it can happen that when you are declaring a target and you depend on another target, that other target is still not declared. And in a lot of the functionality that we have built in, we may need to extract some information from that target that you're depending on. So in those scenarios, what we do is we save that information, we store it in a variable, and then later on at the end, when we have all the targets declared, we go and create those relationships. And we have functions that basically are able to abstract and make things easier for you. So this is kind of like the main one. This is our Swiss Army function. And it's what you will use to add any target. So we call target to a static library, a dynamic library, executable application, etc. So the first question that I always get here is, why do we have this function instead of just using raw CMake? We try, and we ended up with a couple hundred lines in every time that we need to do a target. And I'm going to show certain things that you always want to do when you're declaring a target, and basically this function is abstracting you that functionality. So this function is going to let you declare a static library, a header-only library, modules, etc. Pass build dependencies, declare include paths, etc. So one of the things that we are doing with this function is for you to be able to, when you're declaring your target, to define a file where you're going to have all the list of files that you want your target to have. This is very common, and it's very useful because you want to be able to version that file separately. You want to be able to, in a code review, see the files that are added, remove it, etc. And you don't want that list of files to be interleaved with the declaration of your target. It will make the declaration of your target quite long from a text point of view. So what we do is we have a parameter called file CMake, where you pass a file, and that file contains the list of files that is going to be in that target. So in this case, we have the camera underscore file CMake. And if you look it in the file system, that is in gems camera code, camera underscore file CMake. So it's basically right there. And it has the list of files that are going to be part of that target. And then we have another case of the camera target, and that has also a list of files. In this case, it has just 2 files. One of them is a CMake file that is just added so we can see it in the IDE. And the other one is the CPP file. It also lets us do some other tricks. Like, for example, we have a third-party system. And what we want to do is when you depend on that third party, we want to go and download a package that contains that third party already built. So this is something that CMake doesn't bring out of the box. And what we are doing is when you pass a target that it's named third party : you can see here on the right, on line 477, we detect that. And then we download that package that is on 481. And then we call find package that is a CMake find, that is a CMake function that basically goes and includes that find file from the package. And then we have some association part where we say this target is associated to this package, and that's how we find what to download. So doing this manually for every time that you want to do a target, you will find yourself, okay, I'm doing this like all the time. Why don't I abstract it behind a function? And that's basically what we did. It also let us handle multiple platforms. So the way that we handle multiple platforms is with this concept that it's called PAL, Platform Abstraction Layer. And what we do here is basically, if you see on line 29, we basically are saying, okay, include a platform underscore current platform underscore files.cmake. And that, in the case of Windows, that expands to platform underscore Windows underscore files.cmake. So that will include the files for Windows into the current target. So if we are in another platform, that will point to another file that will have another list of files. And we can also not just include different files, but we can also set different things for this target. So we have the second file here on the bottom right. We are setting different build dependencies for Linux. So in this case, we're making this target just for Linux to link against pthread, unwind, DL, and atomic. The functions on line 12 and 13 are a way to find those platform folders. And we do this because you could have certain platforms in another folder structure. This is what Colin was talking yesterday in his talk. This basically gives you the directory to where that platform is, even if it's not relative to the current path. It could be relative to some restricted path that is in another structure completely different. And we have a similar way to abstract platforms in header files. You may have seen this. In this case, when you include the platform include underscore platform.h, that ends up including a file that is in platform/windows/AC core. And the reason why it ends up including that is because here on line 35, on the left, we pass that as an include path. So when you go and include that file, it's going to find it in platform Windows instead of finding it in another platform. And then that file ends up including the actual implementation that we want for that platform. We also have some other behavior that we built in. One of those is runtime dependencies. So CMake doesn't have this concept. So let's say that you have an executable or a library that ends up doing like a load library or a process exec of some other process, right? You're not depending on that for linking. You're not depending on that for an include path. But you need that thing to be built and to be next to you or in a certain place to be able to execute it. So for example, if your target is a bundle in Mac, you want that, and you are doing like a DL open of a library, you want that library to be in a path inside the bundle where it's going to be found. And that's what runtime dependencies do. You basically say, I'm depending on this target runtime, and that will, under the hood, what it does is injects a post-build step where it's going to make that copy. And here I am showing a generated file. So basically, we generate this file that it's going to do the copies. You don't need to understand too much of this, but if you find an issue, you can dive into the generated file and see if it's generating something empty or if it's generating a wrong path or something like that. It also lets us do some other tricks, like how do we build monolithic. So in monolithic, what we do is instead of making our gems are plugin systems. So when you declare a target inside a gem that is a gem module, that is basically we're going to load it dynamically at runtime. And we generate a file that says this project is dependent on these gems, and that is going to trigger the dynamic loading. So how do we generate monolithic? We basically, instead of saying, OK, for this target, generate a dynamic library, instead of saying that, we say, for this target, generate a static library, and then everything gets wired together. Instead of loading it dynamically, it's going to link against it, and the only thing remaining there is how it gets hooked up into the game, which we are doing by generating a file that gets added to the project, to the game project. Sorry, to the game launcher. Yesterday I talked about the different build workflows and how the engine ends up including the project. So you can see this in the root CMake list file. There is a include CMake/projects. And then inside that file, you will see that there is a for each there for every project in ly_projects. And there in the last line in 146 is where it ends up including that project. So everything that we are doing is all there in code in CMake. So you can just refer to it directly. And in the project-centric engine source workflow, when we said that the project finds the engine, basically that find, it's there on line 9 on the top right. And then that initialize is where it ends up including the engine. And then the engine including back the project, it's where we saw it in the previous slide there. And I talked that we have like an if-else there in the project to avoid getting into a loop. And that is the if-else that you can see here in the top right. And we also talk about the project-centric engine pre-build and how we can generate an SDK that will look very similar to the engine. And I wanted to put here a comparison between the CMake file that is in the engine source and the CMake file that we generate for that SDK. So on the left, you can see the target AC core declared from a source point of view. So the important thing here to note is that we are adding these file CMakes where we have lists of files that get included for this target. And on the right, we don't have that. We basically have some code here at the bottom that includes other files. And in those files, you can see, so this is in the bottom right, you can see that we are setting a property called imported location. And for profile, we set it to the actual accore.lib file that we are building. So this is how we end up declaring that target in wrapping that already built library. And we are generating that file during the CMake install process. So from an outside point of view, looking at the, from an outside CMake point of view, looking at the engine source or looking at the pre-built SDK, it's the same. You're seeing a target with certain properties in both sides. The only difference is that internally that target represents either building or just importing that library into the, as a target. And the install process just creates a target that it's installed. So we went over that yesterday. We use it to generate the SDK. It's not limited to generating the SDK. You can call install on projects, for example, and it will try to generate that output. We may use it for other things. So you could generate today an SDK that contains your project as well, for example. It's not something that we are trying to do as a workflow, but because we already did it for the SDK, it doesn't matter which targets are inside that thing that you're building, it will still apply. So if you add other gems to your engine or to your project, all that will get installed if you call it CMake installer on it. It supports multiple configurations, so you can create an install SDK that has different configurations, and you can see that here in that for each loop on the middle right. We are iterating over the different configurations and including those files optionally. So what happens is that when you build the different configurations, that file will get or not generated depending if you have that configuration or not. And it will, we have work in progress to be able to support build permutations. So that is to be able to do, to be able to have like an SDK that is half non-monolithic and also supports monolithic builds. So we will be able to enable that soon. And that, the way that we are enabling that, we already have some of that functionality in. If you look at line 5 there on the bottom right, you can see that there is a default there. So it's profile/default. When we are building monolithic, you will see a profile/monolithic. And basically that for each loop that is on lines 31 to 42, it's going to have an if-else that if it's monolithic, go to this file, if not, go to these other files. And for the installer, we are using CPAC, which is part of CMake, and it works very similar to CMake in that it uses a generator. So you can also add your own ways to package your projects or to your SDK. Right now, we have just one generator that is using Wix. But you can go there and create your own integration and put your generator there. and package it the way that you want. There are some generators for CPAC that come with CMake by default, and there are some others that you have to integrate them, but it's possible. You can integrate them. Okay. And that's it. So any questions, please post them in SIG Build, and I'm going to try to address them. Thank you.